Yes.
Good evening, everyone, and welcome back to Morocco HPC's webinars. It's really great to see you all here today, especially since it's been really a long time since we had our last session, and we're really excited to restart the series with a topic that is at the same time timely and essential for the future of computing. So at Morocco HPC, our goal is to bring together a community that is passionate about HPC, AI, and advanced technologies. And we also aim to create a space where we can learn from each other and we can learn from experts in the field. Today's webinar is titled Energy Efficient Architectures in the Era of Massive Data Processing. As data processing and AI workloads continue to grow, the question of energy efficiency is becoming central. How do we design systems that are not only powerful, but also sustainable? That's exactly what we will be exploring today. So we are really happy to welcome Dr. Safa Dahmani, Associate Professor at Institut National des Postes et Télécommunications, and a specialized researcher in computer architecture, parallel systems, and HPC. Dr. Dahmani brings a rich combination of academic and industry experience. Her research focuses on energy optimization and intelligent evaluation mechanisms for both embedded and large-scale high-performance systems. We are really happy and excited to have her with us today, and we're really excited to see her share her insights on this important topic. As always, please feel free to drop your questions in the chat during the talk. We will be happy to address them at the end during the Q&A session. Safa, thank you very much for accepting the invitation, and thank you very much for joining us today. It's really a pleasure. And without further ado, the floor is yours.
Thank you very much, Safa, for the introduction, and good evening, Imed. Good evening, all the community that is present here today. I'm happy to present this small talk about energy efficiency architectures in the era of massive data processing based on the work we are actually doing with my team on that topic. And I'm really happy to share that with the community and discuss about the different challenges, different solutions that are part of the state of the art today. So let's start with a small introduction to the general context of this topic. So as we all know, there are modern workloads requirements that are becoming more and more computationally and data intensive. And we can distinguish different types of workloads like high precision modeling, which is the case for industrial and physical, real-life physics simulations, such as CFD, weather forecasting, and really real-time high deterministic systems. We talk also about workloads with very complex operations, such as based on vector and matrix, parallel computing, and with the increase of parallel systems and the parallel capacity of these systems, those operations become more and more complex to optimize and more complex to deal with. On the other side, we have data-centric challenges that comes mainly with the specific applications. We have to deal with massive data scale, going to petabyte scale data sets requiring very high bandwidth, very high memory requirements, and also high bandwidth network abilities. We can add to that what we call irregular access patterns while dealing with graphic analytics, dealing with neural networks, and all this complexity is bringing really very complex requirements for our HPC systems. So the main question is what we have currently to deal with all these requirements. So on the HPC systems, we have the exascale challenge to take, and recently, I mean, I will present a brief description of that later on. But we currently have 4 exascale machines in the top 500 HPC systems. So we are having a real transition from petascale to exascale, which has made power consumption the primary design constraint, and we will see why. From the data-centric or from the data perspective, we have real issues related to data-centric bottlenecks. We have massive data processing that leads to the power wall, in addition to the memory wall, the traditional memory wall problem. So here we have a real issue with data movement between memory and processors that will consume very high amounts of energy, than sometimes which is more sometimes it is more expensive than the actual computation. And also, in the previous slide, I've talked about the complexity of the workload itself, the computation itself. So we have a real diversity of workloads that modern HPC systems have to deal with. So they need to provide a certain balance between compute-bound and memory-bound applications, which is not a very easy task, especially if we take energy consumption and power consumption in consideration. So this issue related, or this scalability issues leads us or oblige us in certain form to deal with some sustainability metrics, such as the energy efficiency. Oops, sorry, I have to go back. Such as the energy efficiency, which I will present in this comparative table. So I've taken this table from the official websites of the top 500 HPC systems and top green 500 systems. So here we have the first most powerful HPC systems in the world. According to the list of November 2025. So we will see that first let's have a look on the performance. So we see the first top machine, 4 top machines that are on the exascale. That are exascale. So and afterwards the performance is going down, but on the power consumption we will see that the power consumption is becoming really high while dealing with the exascale. And the energy efficiency is really very variable for these systems. So this classification is based mainly on the performance. So if we take a look on what is the ranking, what is the ranking of those machines on the green 500 list, we will see that they are not doing that good. You know, like for example, El Capitan, which is the first, the top 10, is ranked as 23 in the green 500, which means that we are really focusing on performance more than energy efficiency. So the graphic here is showing a comparison between the top 10 of HPC machines that are designed with the blue lines, presented with the blue lines, and the green lines are representing the top 10 of green 500 HPC machines. And on the left side, we compare the performance. We see that I just want to mention that the scale here is logarithmic, so we cannot have a really big gap between both. But we already see that there is a really huge gap between performance in the machines that care about energy and the ones that don't. And on the other side, we do a comparison between power consumption, and it's the same thing. So this analysis shows us that there is first a dynamic performance range between both types of machines, so which can go up to 3 orders of magnitude. So we're going from really very few petaflops to exaflops. And on the other side, we see that there is a real power penalty. So while top 10 systems offer the highest throughput, on the left side, we see that their power consumptions can go to 800 times higher than the systems that really care about energy efficiency. And from this analysis, we can see that there is a really big issue about energy consumptions and how systems are dealing with it. It's clear that it's not a real priority for the current powerful machines. So automatically, when we care about energy, we lose performance, which means that we're not really developing very energy aware systems. So based on the November 2025 top 500 and green 500 data, energy consumption in supercomputing has reached a very critical inflection point. So the green 500 list highlights that while some systems made significant strides in energy efficiency, the majority of the new installations, the recent ones, are really leading to a growing energy footprint in the supercomputing landscape, which is really not good. And I will see what, because we really want to do supercomputing. We need it. It's a real requirement of the modern applications. But the question now is, at what cost? Are we ready to pay the cost for such computational power? So let's see what is the cost of all this. The numbers here are really based on an estimation cost from the national. I will show it. Yeah, they are based on the most recent International Energy Agency averages for industrial consumers, which is issued from 2024 and 2025. This is the most recent one I could find. So let's see what's happened for what is the cost for these performance machines. So here we have the energy consumption in kilowatts, and the annual energy consumption in megawatt hour, and the cost is around, as you see, is around 32 millions, or more than 32 millions for the Aurora machine. And the Jupiter Booster machine, which is the one that is, I mean, the best for energy performance balance, it is around 30 million, more than $30 million a year, which is a bill that is not neglectable from a financial side or economical side. In addition to this bill, there are some invisible infrastructure costs, which are first the cooling overhead, So the actual utility bill is up to 20% higher than the IT costs shown above. So we have to add 20% cost to the one that is already calculated here. Plus, in some countries, especially in Europe, the HPC sites must factor in carbon credits, so they pay more money for their the CO2 emitted for each machine, which is bringing the price or the bill to a very high level. So, sorry. So now to finish with this introduction, it was really a long introduction, but it was very important to highlight that even though we need the performance abilities of these machines, we are not we will need more. And I mean, in the future, it will become really very important to reduce the price and the bill of using these machines, because most of the industrials will not afford the bills behind all these computations, especially with the massive use of these machines. So now the question is, what can we do on the architectural side? So I will present a few techniques from the literature. Let's start with what we call DVFS, dynamic voltage and frequency scaling, which is a technique that is meant to reduce the energy consumptions during the low utilization of workloads. I mean, the low utilizations of the processor of certain phases in the workload. So what happens is we have, I mean, now we have more. We're using more and more heterogeneous architectures. So for some workloads, so depending on the workload, there will be phases where we are really using the different cores for the different computations. We're using memory accesses, etc. And there are phases in the workload that the core utilizations is lower. So the idea behind this dynamic voltage and frequency scaling is to reduce the voltage and the frequency, while we don't really need them to be high. So it can bring up to 22% energy reduction with only 3% slowdown, like for example, for the NVIDIA architectures, which is a very good level of gain. So the mechanism is very simple. There is direct learning from raw performance counters. So we read metrics from the counters of the machine, for example, cache misses, IPC, and we apply proactive frequency caps to limit the frequency and the voltage depending on each phase we are using, in which phase we are during the workload execution. So I found an example for the Frontier supercomputer, which is a very performant supercomputer. The data reveals that software-driven DVFS applied to this machine achieves up to 8.5% savings for resource-constrained jobs, which is the equivalent of 1,500 megawatt hour saved over 3 months. So it means that we can do a very, very good energy saving using this technique. Another technique that I would like to present today is the power gating. this is it's almost the same concept, but it's here it's applied to the directly to the cores and the links. So the concept is to shut down idle cores or links in the network through power gating, and reactivate them on demand to match the workload intensity. It's the same. It's based on the same metrics. So we are going to watch the workload intensity variation and then adapt the cores and links power depending according to it. So it will eliminate static leakage while preserving performance, because we will use the cores whenever we need them, but also we will shut them out when they are not really used. So another way to optimize we can do it in a static way, but the best way of exploring this technique is doing it dynamically. So through an online supervised learning model that can predict future resource needs from hardware counters and workload dynamics, then it will toggle core and links power domains online. So while executing, so on the runtime, we can manage and handle this on and off on the cores and the network links. For example, one of the interesting results they have found in the literature is a topology-aware applied on energy reduction applied on Taurus network through the technique of power gating. So we will shut down the links on the Taurus network when they are not used, simply when they are only when they are not there is no heavy traffic on them, and then shut them up and then enable them or activate them when they are used again. So this power gating technique have some weaknesses which depend on some considerations in the design, such as transition latency that must be hidden within the task scheduling windows to not really cause some penalties regarding the computation itself. And we should also consider the thermal budget of monitoring and taking decisions online, and also to prevent premature reactivation that could cause some throttling. So we should avoid the fact of enabling, disabling cores in a very short time, which can make some issues and some degradation in the performance of the system. And sorry, just to mention something, this power gating can be applied also using DVFS, the previous technique. They can both be applied on the same system, and they show the very interesting results if they are joined, both of them. So another architectural optimization that we can have is intelligent task mapping. So you know now that we are using very frequently or very often we're using heterogeneous architecture. It's becoming like the new normal of using CPU, GPU, some specific accelerators in your system. And the main question that comes with this heterogeneity is how to map data to the different compute nodes. And here we can do some optimizations related to that can lead to energy optimizations, such as data flow driven mapping. So we transform, for example, CNN models into synchronous data flow SDF graphs that expose task and data parallelism, and then we place each kernel on the most energy efficient processor that is suitable for the kind of computations or operations that are done by this part of the graph. So we will adapt this mapping to the efficiency of the computational node considering the type of operations, the type of the part of the workload that is managed by that. Another optimization that is that was found in the literature, which is using genetic algorithms optimization. So, which is mainly an optimization dedicated for multi-objective optimization issues. So the idea is to find a Pareto optimal mapping that jointly maximize throughput and minimize the energy, while also selecting voltage frequency settings, VFS, for further savings. So we can take profit of the previous technique that are really very low level ones with high level optimizations run by adaptive algorithms such as the genetic algorithms to try to find the maximum balance between the maximization of the throughput and also the maximization of the energy efficiency. Another point will be the criticality aware scheduling, where we consider the criticality of the task. Here we have an example that was applied on Big Little Course machine, which is using dynamic DVFS and task clustering based on the criticality of the different tasks. So the paper, the references doesn't appear on my on the frame, but there is a paper describing those results that shows that we have up to 6.8% power reduction and 26% temperature drop versus the baseline configuration. Which is really a considerable and interesting results. Another point would be the runtime aware remapping, which means that we will adapt the mapping online based on an online monitoring of the system, considering the core utilization, the cache misses, the temperature in the system, and other many other metrics. And based on that, we can trigger remapping of jobs to cooler or less loaded nodes, and in that way we can avoid the hotspots in the system, and avoid really many issues related to concentration of computation on certain parts of your system. So all of these techniques are really adaptive techniques that can be optimized more using some intelligent learning techniques, and this leads us to really a summary of those all of these techniques that were presented before. So we have DVFS, which is a proactive and adaptive workload-aware frequency capping, using we can use as a technique, as I said, intelligent learning, and have really very important and very high energy savings with minimal performance loss, because it's important to keep the performance abilities as mentioned in the beginning. So we have the technique of power gating, and we can do it also dynamically based on some predictive models that can eliminate static leakage and enhance the insights on the behavior of the workload, the behavior of the hardware, and then join both of them to make intelligent decisions online, and naturally try to reduce the latency, reduce the thermal, the heat dissipation, and also manage in a very efficient way how the system consume its energy envelope. And also the intelligent task mapping that we have talked about earlier is something that we can do intelligently also. So using data flow driven mapping and criticality aware scheduling, we can optimize the energy efficiency and also reduce the communication penalty between the different tasks. These three main techniques, that we summarize in that frame, shows us that we have different low-level optimizations that in the literature that shows very interesting results. But the question is how to join all of these techniques and how to create a system that can give us a maximum energy efficiency while really reducing the performance loss, especially from data or memory bounded systems. So to answer these questions, we have been through some new architectural paradigms that are near memory and in-memory computing. These two paradigms, or we can join them to a single one, which is in-memory computing, if you want. That seems to be very interesting from an architectural perspective. So let's explain what is processing near memory first. So it's the fact of integrating processing elements near the memory models. So the PNM can achieve theoretically up to 10 times energy efficiency improvement for memory-bound workloads by performing computations next to data storage. So we are trying to avoid the traffic, the spread of communications through the network, and then we are gaining energy. So we have also the in-memory computing, which is the PIM, processing in memory or in-memory computing. Which is the fact of directly processing some operations in the memory. So we are using the microprocessors inside the non-volatile memory, for example, inside the DRAM, to perform some logic operations within the memory itself. So this will really eliminate a huge part of the communications with the DRAM that are, as presented in the beginning of this talk, that are representing the real memory wall that leads to an energy wall. The challenges using these two techniques is that both of them require new programming models, require hardware architectures, new hardware architectures, new system software to manage the scheduling, for example, to manage the communications, to manage the memory storage, and everything need to be reconsidered in your architectures. But they are really two concepts that are very promising. So that's what we are working on currently in my team. We are trying to develop benchmarks and we are trying mainly to develop some framework that are based on PIM integration in the hardware, in the architecture, and then implementing benchmark on the top of it to prove that this is something that very promising for a huge bench of applications such as automotive applications. So I'm going to explain why this is a promising energy-aware architecture solution. So first, because we are trying using using the PIM concept or the PIM paradigm, we are really reducing drastically the data movement. So we are eliminating the data movement bottlenecks that was really a big issue in traditional architectures. So when we say data movement bottleneck, we say energy cost, very high energy costs, because every communication it costs lots, and also communicating with the external memory with the DRAM is really something very costly, very costly, very expensive. So if we can get rid of some of these communications, we for sure are going to optimize the energy envelope of the system. So the energy efficiency potential is really, as I just explained, is really based on eliminating the need for frequent data transfers. So PIM can achieve orders of magnitude improvement in energy efficiency for certain applications. It can make really a very sustainable solutions for HPC systems, especially in the era of massive data processing. Another problem that we can resolve with this kind of architectures is the scalability problem of, especially considering the complexity of workloads. So the PIM architecture can handle the growing complexity of workloads because it will divide the computation into simple operations and complex operations, and it will really focus on accelerating the processing of very simple operations within the memory itself, and then let the system deal with the complex ones in a very, lightweight approach. And then we have the emerging memory technologies that we can take profit from. So as we all know, we have now some new we have some new technologies in the literature and in the industry also, such as the 3D stacked memory, which is really very optimized for energy. So here, PIM can take profit of these kind of technologies to optimize the memory more and more. So it can enable more efficient and scalable PIM implementations if we really use the memory technologies that are really optimized in terms of memory, which will further enhance its viability and its sustainability for the future of other architectures. So for all these reasons, PIM stands for as a really promising energy-aware architecture. And in my team, as I explained before, we are working on some solutions for automotive systems. So we are really trying to join between the HPC world and the embedded world, as now one of the, the big points that are joining both worlds is the fact that both of them are dealing with data-intensive applications. So in the autonomous and the smart vehicles, we now need to process a huge amount of data because of all the sensors that are in the car, in the vehicle, and all the functionalities, the smart functionalities that helps the drivers. We do need really a very important and very heavy performance or computational power. But on the embedded side, the big issue is that we have a really constrained energy envelope. We don't have that big energy budget. And to deal with this, it's very important in every single architectural decision in the design of your system, that you take into consideration this energy and power constraints, budget. And so that's why we are trying to implement some solutions based on PIM, especially on the hardware software co-design phase. So we're trying to integrate this PIM paradigm as early as possible in the design. So to take it into consideration while doing the task mapping, and while doing all the decisions regarding the positioning of the different components, the type of interconnects that are the buses that are used to for communication inside the system, etc. And what I wanted to say by doing this deviation to the embedded world is that there is more and more common points between the HPC and the embedded world. Traditionally, when we were talking about HPC, we say, no power budget, no energy budget. And when we are talking about embedded systems, we are really thinking about budget, volume, really very big issues around these parameters. But now HPC is exactly at the same line as embedded systems. We do need to care about the energy consumptions because of all the reasons I explained in the beginning of this presentation. So here is a really quick case study where PIM can be interesting for graph analytics applications. So the graph analytics workload are characterized mainly by the regular memory accesses and high data movement, so which make them ideal candidates for the PIM, because PIM is meant to reduce the data movement and deal with the different access patterns. So PIM implementation for these kind of applications can be a simple DRAM-based PIM units that can perform graph traversal and aggregation operations directly within memory, reducing data movement by up to 90%, which means that we really can make a very interesting improvements in energy efficiency. And also, we have to maintain, as I mentioned before, the performance gains that are traditionally taken from heterogeneous systems like CPU, using CPU GPUs for large-scale graph analytics tasks. So this is one of the case studies that we're working on. We're working on also some specific algorithms to the automotive world, such as the YOLO algorithm. So currently there are works in progress that we couldn't present here, unfortunately, because it's not yet completely finished. So we are trying to implement a bench of applications on the PIM architectures using simulation, and to extract an important data set that will give us a very good knowledge of these workloads that are really giving interesting results using PIM. And then this knowledge about these workloads will allow us to create an intelligent framework that will make decisions knowing the specifications of each workload, the specification of the architecture, considering including the PIM, the PIM technology, and then make decisions on which task mapping what is the best task mapping to have, what is the best configuration of your architecture we can have, like for the bus bandwidth, for the number of computing unit we need, how big the memory we have, and also to reduce as much as possible the the external memory accesses that historically were taking a huge budget from the computational power of our systems, because as we all know, the access penalty to the DRAM is very high compared to a cache access. So now the idea is creating like a whole framework that will help us building systems from the application to the architecture that are intelligent, adaptive, and will take into consideration, on one hand, the workload specifications, and also on the other hand, the PIM architecture, or the architecture specifications. And we believe that this is something that will give us really very interesting results and very good results. The future directions of the work, the actual work, is first scaling heterogeneity. So the idea is to combine traditional CPU and GPU processing with PIM to leverage the strength of both paradigms for different workload characteristics. That's what I just explained. So we need to create our own data sets based on multiple simulations and multiple benchmarking on using the PIM-based architecture. And then from this knowledge, we can create intelligent learning engines that will help the user to make the right decisions depending on what he would like to privilege. If he would like to privilege the performance, the energy efficiency, he will make his decisions depending on what really is needed in his use case. So the second point is system integration. So addressing the different challenges related to integrating PIM. So PIM is a paradigm that is coming with its own challenges. One of the biggest challenges is the memory management, is the task mapping, is also how to make the right decision of doing the computation on the DRAM or doing it on the CPU, while considering the performance gain and not causing any loss in the performance. Another point is the energy-aware scheduling. So designing energy-aware scheduling algorithms that can dynamically allocate tasks between traditional processors and PIM. So this is kind of decision maker online that will divide the task workload between the PIM and the traditional computation units. And then, as every new paradigm, we do need the programming model that comes with the new architecture. For the moment, for our simulations, we are doing bare metal implementations. So we're really playing with the instructions of the processors that are implemented in the DRAM. But in the future, it will be very interesting to develop new programming models to integrate them to the traditional programming languages to support PIM and adopt it, make people adopt it in most HPC applications. So to be easier to use the PIM concept. So this was the main point of the presentation. If you have any questions, I'm happy to answer. The discussions are open. As I said, we are still developing new thing about it around these concepts, and also we're still having results. I forgot to put 2 journal papers that were published this year regarding the subject, and they are one is the state of the art of the architecture techniques that will be published. It is accepted, but it will be published next month, I think, on May. And another one that is introducing the new PIM architecture, a new PIM co-design, hardware software co-design framework for automotive applications. This one is already published. It was published on March. So I invite you to take a look on these papers to have more insight on what we are working on. And yeah, I'm open for any discussion, any question. Thank you very much.
Thank you very much, Safa, for this amazing presentation. For me, it's always impressive to look at the compute energy trade-offs, because traditionally they go hand in hand, like more performance requires more energy. But as you said, we can no longer tolerate that. We can no longer afford that, because it's only getting the compute demand is only getting higher and higher. So we cannot really afford spending that much energy on all the compute tasks that we can have. Thank you also very much for explaining to us the work that you are currently doing. It's extremely interesting, and congratulations on your accepted papers. And it's really, really interesting to see that there are actually ongoing work in this direction, in a direction that will allow us to work in an energy efficient manner, but still get the performance that we need. I invite the attendees to drop their questions in the chat, and then we're going to read them to Safa. Ahmed, do you have any questions or any points you want to discuss?
Yes. Thank you very much, Safa B and Safa D for the presentation. It was very informative. So I learned a lot of things. So I have started working on the subject since 1 year ago, and we started only by the CPU. How for example we can reduce energy consumption on CPUs while keeping let's say the same performance. We cannot do that, but we can at least avoid losing a lot of performance, and we achieved a good point. So we reduced the energy by 20%, and while we lose only 4% on performance, but it was only on let's say on CFD and CFD problems. But and we have found some problems in it was only offline model, so we did not success to get online model, because we did not have we did not run a lot of benchmarks, and since we did not find open source library that can allow us to do a lot of benchmarks, since we need data to train offline model and to construct this online model. I don't know if you are aware about some open source tools that can maybe help on that. So this is my first question. And my second question is about GPU. So in my knowledge, GPUs don't have the DVFS paradigm. I'm wrong. Am I wrong, or I think they have another thing, no? Because when we have tried to do some benchmarks, and even for memory transfer, the GPU can increase the frequency of and we did not understand why, because maybe for the GPU even the memory transfer for it is needs high frequency. I don't know if you also got this behavior. But this is what we found. We did doing some benchmarks. We found that even for memory transfer, we we have the GPU increase the frequency, but I don't know if it is DVFS who does that or another thing. So yeah, this is mainly my two questions. Maybe I have another one, but maybe I can.
Okay, just Ahmed, if you can just repeat the first question. Is it about the simulation tool, an open source simulation tool, or?
Yes. Yes.
Yes.
We did not find like like simulation tool that can help us to yes, to run simulations, to gather data, to train our model, because yeah, we found only, for example, single nodes. We with few doing like MPI, we cannot like we did not success to do like a lot of simulations to gather data.
Okay, which one are you using actually?
So we have used the one we used, it's my like open source library called Manapi for CFD. We found a tool called Rodinia, but it handles a lot of benchmarks in single GPU. But for CPU, there are only few. But same thing, they are not like handling MPI communications. So yeah, I don't know if
currently we are using we are going through a Gen5 simulation, and not the I mean, we are using a DRAM component based on Gen5 plus a PIM architecture component also associated with Gen5. So Gen5 has a lot of benchmarks that we can go through. So we're using these benchmarks, especially the ones dedicated for automotive applications. So far, it's good. It's given us the metrics that we need. I don't know for CFD applications if there are things already implemented in Gen5, but I think as Gen5 is widely used in the research world, I will be surprised that nobody has already implemented this it on it. So I will see. I will do a quick research and tell you if there is opportunity to do things using CFD, using Gen5, considering CFD workloads. But yeah, we are using Gen5 mainly. Plus, as I said, the DRAM components and the PIM components of Gen5, which are completely independent simulation components. Not independent, they are based on Gen5, so you need to use them with Gen5, but they build they are built in separate way.
What are the benchmarks in Gen5? What are it's like what matrix multiplication and stuff like that, or?
Yes, exactly. And we to be honest, we are implementing our own ones.
Okay.
They are Parsec that is available on Gen5. There are some examples in the PIM component that we are using, like vector, some benchmark based on vector operations, matrix operations, etc. Very basic ones because it's bare metal, so it doesn't give like a huge freedom in and easiness in using in implementing new very complex algorithms, but that's what we are working on. We will try to enrich the instruction sets, the ISA already implemented in this component, the PIM1, to be able to implement complex things. But yeah, it's ongoing. It's in progress. For the moment, we're starting with very simple things. But yeah, the purpose is to go through it to build something more complex.
Okay, thank you. So.
And what was the other question? I forgot it already. Sorry.
No, that's fine. My second question was about the DVFS. So the problem, in CPU. So the problem with DVFS in CPU, it's that, for example, if we use in demand, once your workload increase, the in demand increase the frequency to the highest one. okay, so we noticed that doing some benchmarks. So we have proposed something. So, but it does work only for, as I said, we did that only for safety problems. And we got like some remarks from your viewers saying that if you want online model, you need to simulate over different benchmarks, not only safety. That's why we are looking for new tools for doing benchmarks in other domains. So the thing that's in as I said, in GPU, so the problem is that even if you do transfer, memory transfer, so we noticed that the frequency is higher, even for and we did not understand why it behaves like that. I don't know if you have any idea about it.
I don't have an idea about to explain this, but I already saw this somewhere. But the information the data I had in my presentation is based on work. I will send you the paper on the work that was developed in, I think, 2017 or something like this, where they try to integrate the DVFS on some NVIDIA architecture, GPU based, and they report that they have very interesting results regarding the memory, the energy consumption. So I don't think it's open source. I don't think we can have access to their system, but
this is actually what we are trying to do with within my team. So it's like to develop DVFS technique on the GPU, because we did not find something already.
There are not open source implementation of that.
And NVIDIA so far they are not using DVFS in their GPUs. We don't know why.
I think the VFS it's somehow seen as a treat for performance. So we don't want to have this performance loss, the risk of losing performance if we implement it, if you enable it by default on GPUs. The risk is that is this, but yes.
Another thing that we did not find, for example, we did not find in the literature something that deals with, that now, for example, if you deal with CPU and if you run some benchmarks on the GPU, you need to pass through the CPU to define your tables, etc., and then go to the GPU. And we did not find something that deal with both at the same time. Means adjust the frequency in both GPU and CPU at the same time. Because once you transfer your information or your data to the GPU, you more needs like a higher frequency on the CPU because you are doing nothing. And the same thing, once you go back to the CPU, normally the frequency on the GPU should be decreased. But so it's something also that we are working on. But we still don't get any interesting results. We are still because we are struggling to develop things from scratch. We did not find something already done. This is the problem.
I can see. This is the same issue with us. We are having a huge delay on our results because there is only one PIM is not really very available on industry. I think there is a Samsung chip and another chip, that only two chips on in industry that are supporting PIM. And for the simulation, there is only the one that we found that is kind of good, and also we have the direct contact of people that are developing it, so they help us a lot in understanding things. But still, the open source available tools are not complete, and they don't provide very easy ways to implement new workloads and new applications. So we're doing things ourselves and trying to build things from scratch, which is not easy, and also which takes a huge amount of time. So
Yeah. Okay.
This is good because it means that there is also much to do.
Yeah, sure. So yeah, it's my last question is regarding the PIM. So do you think that for like new supercomputers will like integrate this technology on their processors or in
Yeah,
their
as I said,
RAM?
there are ARM processors that integrate this. I think there is one ARM processor, and I think there is a chip that that is available in the market, which is the Samsung chip one, where PRIM is implemented on the 3D memory. And this is the model that we're using, but not really the real chip, but through the simulation.
Okay. So thank you very much. I'm done. Thank you, both of us.
Thank you. Thank you, Ahmed.
Thank you, Ahmed, for the great discussion. We actually have a question from the audience. We have Anas, who is asking, on the DVFS slide, you mentioned that traditional governors can lead to energy leaks in non-critical execution paths. Could you please clarify what is meant by non-critical execution paths?
So the idea is the critical path means that there is a huge and heavy, intensive computation in the flow. So when it's not non-critical, so it's considering, like, for example, the amount of computation is very low, or the communication are between the CPU and memory are not very high, etc. So this will lead, if we don't use the DVFS, if we don't reduce the frequency, and we work at the same level of frequency, it means that we are losing energy without a huge amount of energy without really needing it. So that's what I mean by non-critical execution path. It means that our execution part or execution part of your workload where we don't really need huge effort from the architecture perspective.
Yeah. Thank you very much. Thank you, Anas, for the question. I hope this was clear for you. Thank you very much, Safa, for this amazing presentation. Thank you very much for the insights. Thank you for walking us through your work and what you're trying to do with your team. Best of luck to you in the future paths that you're trying to work on. Anas is saying, so when the workload is not compute bound. Thank you. So he understands your answer. Okay, thank you very much, Anas, for the question. Thank you very much to all the attendees who joined us today. Thank you very much, Safa, again, for accepting our invitation, and we'll see you in the next webinar.
Thank you very much, Anas and Ahmed and Safa. So it was really my pleasure to share with you some insights on the subject and discussing with you. I think I'm going with really more questions, more ideas. So thank you very much for the insightful discussion.
Yeah, our pleasure.
It's fine.
Goodbye.
Goodbye. See you.
Bye.